Today we'll be looking at how we can use parallel binary search to solve problems when doing binary search per query is too slow. Before we get started, consider subscribing to the channel to support it and press the bell icon to stay notified about future videos on exciting concepts. The problem we will be looking at today is POI Meteors. The link to it is in the description. You should now pause the video and read the problem once on your own. To make sure that we're on the same page, I'm going to go ahead and explain what we are being asked to do here. So this is a sample test case given on the problem page. We have 3 member states, 5 space stations, and 3 meteor shower predictions. And these are our stations, and gathered represents the amount of meteors we have collected in each space station till now. In the timeline, we have 3 meteor showers, and these are the range increments. And for state 1 we need 10 meteors, for 2 we need 5, and for state 3 we need to collect at least 7 meteors. So let's see what the answer for this will be. So in the timeline, when we go to the first meteor shower, we increment first these two elements by 4 each, because these stations, they are in circular orbit. After this last element we go back to the first element. So this update was basically from 4 to 5 and then from 1 to 2. So then we update these two by 4 again. And let's check if we've collected enough for any state till now. So for state 1, we have space stations at index 1 and at index 4. They've collected 8 in total, but we need 10. So this isn't satisfied as of now. For state 2, it has 1 space station and it has collected 0, and this isn't satisfied either. Now for state 3, we have these 2 space stations at index 2 at index 5, and they've collected 8 in total, which is greater than 7. So the answer for 3 is 1. Now let's continue. Now we have this update. We increment the first 3 space stations by 1. So we get 5, 5, and 1. Now let's check for the first state again. The total meteors collected are now 9, because at index 4 and at index 1, and we have a total of 9, which is still less than 10, so this is unsatisfied. For state 2, we've now collected 1 meteor, which is less than 5, so this remains unsatisfied. Now let's apply the third update. We increment all these elements by 2. So this becomes 3, 6, and 6. And let's check for 1 again. For 1, we have stations at 1 and 4. Their sum is 11, which is greater than 10. So the answer for this will be 3. And you can see that for state 2, we still haven't collected enough meteors. So we know that we won't be able to, since this was the last meteor shower. And the answer for this is -1, because we can't collect enough meteors. Okay, let's now see how we can use binary search to find the answer for a single member state. Now I will be using a Fenwick tree in my binary search to show you what we can optimize in a binary search, but you don't need to understand Fenwick trees or segment trees for the purpose of this video. Just keep in mind that whenever I talk about range updates or point queries, they take O of log of m time each. So now let's consider a single member state. My Fenwick tree will basically allow me to increment whole ranges of this array, gathered array, by the desired amount. So in our binary search, the left bound of a binary search will be equal to 1 and the right bound will be equal to k, which is 3, and the midpoint for this will be 2. So what I'm going to do is I'm going to apply all my updates up to the second one and including it and check. um, let's do this binary search for the first member state, and I'm going to check now if after 2 updates if we've collected enough meteors. And as we saw in the sample input explanation, the answer for this first state is 3, so we haven't collected enough meteors. Now we set the left point equal to mid plus 1, which is 3, and the mid is 3. And then I add this last update to my Fenwick tree. Now we'll have collected enough meteors, so we'll set the answer to 3. But you see, the issue here is that even if I apply all my updates, let's say this is 1, this is k, and this is k by 2, well, k plus 1 by 2, the midpoint. Even if I apply all my updates in this region, which is basically going to be my first step in each binary search, I'll be doing at least k by 2 times log of m operations, and that's just for this much. Now if I start doing this for every member state, we have n member states, then that results in a total of n into k by 2 into log n operations, and without considering any other operations done, this is already a huge bottleneck in our solution, because this part alone is too much for our solution. So now looking at the work we did, for each member state we apply the first k by 2 range updates, and we repeat the same thing n times. If we continue to do our binary search that way per state, we do a lot of repeated work. If we could do this just once or reduce the number of times we do it, we could improve our time complexity by a lot. And this is what inspires the idea for parallel binary search. Since for each member state we are applying those k by 2 range updates over and over again, why not do that just once, and for each member state check if they have collected enough meteors up to that point. Let's now turn this observation into a well-defined process, which is basically parallel binary search. Let's see what parallel binary search actually is now. As the name suggests, we perform binary search in parallel. Now, the way we do this is, let me just make a few rows and columns here. This represents the state. This represents the left bound for binary search, and this is the right bound. So this is basically a segment we're binary searching in. This is state 1, 2, and 3, and initially L is set to 1 and R is set to K, which is 3, and this is there for all of these states. So now what we're going to do is we're going to maintain this other array, queries, which is basically an array of dynamic arrays, and queries of I stores the states which have L plus R by 2 equal to I. So queries of I will store the states which have their midpoint equal to I. And let me make 3 rows. And initially all of their midpoints are equal to 2, so all of these states lie over here. Now what we want to do is we want to kind of iterate from 1 to k, because that's how many meteor shower predictions we have. And at each step, we first apply our update using our Fenwick tree. And now basically we iterate from 1 to k, so from 1 to 3. And at each step, let's say I is equal to 1, then we check queries of 1. If there are any states that need to be answered for, then we do it right now. But before that, at each I, we first apply our update. So let's set this to 0 initially. Let's say we're at I equals to 1. We now first apply the first update, which makes all of these elements 4, and check queries of 1. It's empty, so we continue. Now we apply the second update, and now for each of these member states, we can see that queries of 2 isn't empty. So we iterate over all of those member states and we check if we've collected enough meteors for them. So for member state 1, you can check that we haven't collected enough meteors. So what we do is we set L equal to mid plus 1. Mid is equal to 2 over here, so we set it equal to 3. This is just like the standard binary search we would do per member state, but now we are doing them all together. And let's remove 1 from here. Now we check 2. We haven't gathered enough for 2 either, so we set its left point equal to mid plus 1, which is 3. But for the third member state, you can see that we've gathered enough. So what we do is we set its right endpoint to mid minus 1, which is 1. Because if we've collected enough, then we do L is equal to, if we've collected enough, then R is equal to mid minus 1. Otherwise, L is equal to mid plus 1, because we reduce our search space by half. So this was the first iteration. But before that ends, we also go to queries of 3. We apply the third update, which is 3 to 5 and increment by 2. So 3, 6, 6. But we can see that it's empty. So then we reset, we remove all of these updates. Now we do this once more. This time let's re-add member states to their queries. You can see that member state 1 has a midpoint of 3. So we push 1 into here. 2 has a midpoint of 3, so we push 2 into here, and 3 has a midpoint of 1. So we push that into here. And let's iterate from 1 to k again. We apply the first update. And we check, have we gathered enough for member state 3? Member state 3 has these 2 stations. We've gathered 8, which is more than it's required. So we say that we've gathered enough. And we minimize its answer with 1. And then we set R equal to mid minus 1, which is 2. We can see that L is greater than R for this case, which means that we won't be doing any binary search over this again. We go to 2, we apply its update. We see that it's empty, we continue. We apply the third update. We still haven't gathered enough for 2, so we minimize, so we don't do anything. And we set L equal to mid plus 1, which will make this 4 because the mid is right now 3. But L is greater than R, so we have to solve binary search now. And we remove 2. And now we only have one member state left, which is 1. Have we gathered enough for it? We have 11, we require 10, we have, and we gathered at mid 3. So we minimize the answer with 3, which will be this, and we remove this. So in the end, we will end up with the correct answers. And now let's try to analyze the time complexity for doing this. So you see, in each major iteration, we did binary search on each of those member states. We reduced the search space by half. And since originally all of them had the same length from 1 to k, and in each iteration we reduce each of their lengths by half, we will only repeat this process log of k times. This is base 2. And at each level of iteration, we applied updates. So we had k updates, and each of them took log of m operations. And let's see what the time complexity was for querying each of these individual stations. We at each level, we know that we query each station once because each station belongs to a member state, and at each level we query all the stations belonging to a member state once. And that is basically m stations times log of m operations at this iteration. So in total, the time complexity for doing this is O of log of k into k plus m log of m. This is because we have log of k major iterations, and at each level of those iterations, we do k plus m log of m operations. This is just my Fenwick tree, which you do not need to know for this video. And these are nmk. And so for each station we store, so for each member state we store which stations it has, the number of meteors required, the answer, and these are basically our meteor shower predictions. These are L and R as I showed you, and this is just a helper function to help me update my range. So the main part of the code is this, and also initially all our answers are set to infinity. So I've put while true here, but this will only run log of k times, and this is our queries array. This is a variable to check if we've answered all of our queries. So if all L of i's are greater than R of i's, then we've answered our queries, and then we can stop running this, which is again log of 2, log of k. So we initialize our Fenwick tree here, and I iterate from 0 to k because I'm doing zero-based indexing here, but the answer remains the same. I increment my meteors collected. Then I check how many I've gathered for each state which belongs in this queries array. So I query the meteors at each station this state owns, and I put them in this gathered variable. This check is there just to prevent overflow. And if I've gathered more than what I need to collect, or as much as I need to collect, then I minimize the answer for that state. And then I set R equal to mid minus 1, which as we would do in normal binary search. Otherwise I set L equal to mid plus 1, just like normal binary search. Now in the end, if the answer for some state is infinity, then we know that we never found an answer, so we will print NIE, which is just polished for no. Otherwise we print the answer plus 1 because we were using zero-based indexing. Now there's actually a divide and conquer way to implement this, which is basically almost the same thing, but what we do is we say that we have this whole big range 0 to k minus 1, and we make a bucket of all our queries. Now against this midpoint we check all our queries, and queries which have an answer at this midpoint we send them over to the left half of the divide and conquer, and queries which don't have an answer we send them over to the right half. So we do the search again on the right half, then we remove our updates for this segment. So we first have to apply our updates from the start into the middle, then in the end we remove those, and then we recurse on the left side. Now you don't need to know this, you could just implement it the way I showed you, but in case you were wondering how to do this with divide and conquer, I'll leave both of these programs in the description of my video. And I think this will be it for this video. Thanks for watching. Make sure you press the like button and subscribe to the channel if you learned something new today. I'll be posting tutorials on other exciting algorithms and data structures soon.